Hello, everyone. Welcome to the lecture of Intro to the MOSFET. In this session, I will try to give you a brief introduction of a MOSFET, how it works, and what's the physics behind it. The idea of building a MOSFET actually comes from a working principle of a capacitor. So let's say how the capacitor works. In general, in capacitor have a two metallic plates. In between, we use a dielectric material. And now if I apply a voltage around it, then the positive charges and the negative charges will be accumulated on the surface of the capacitive plates. The same idea is used to build a MOSFET. In that case, we're going to use one metallic structure and one semiconductor material. In this case, I am using a p-type semiconductor. One can use n-type semiconductor as well. But the point is, we have to use one doped semiconductor material. And in between them, as usual, I have to use a dielectric as well. Now, if I apply a voltage, let's say V1, what will happen? The capacitive action will go on. As a result, the positive charges will be accumulated on the metallic surface, and the negative charges, meaning that the free electrons, will be accumulated on the surface of the p-type semiconductor. And these free electrons have some special name. These electrons are called channel. This term is quite important throughout the theory of the MOSFET. Uh, well, one may ask that, well, this is a p-type semiconductor. Then how do we get the free electrons? Well, p-type semiconductor has a minority carrier. So when we apply a voltage, those minority carrier will pop up on the surface of the p-type semiconductor. So, well, nothing new, nothing special is happening at this moment. It's a old capacitive action. To explore, to get a new about these things, and we need to explore about it. So we need to create a new connection around around the semiconductor, and is following. In this figure, you can see I have created one more connection and use one more battery around the p-type semiconductor. As I've said, we already have created our channel, which is a free electron, and then we have connected a battery around these two terminals. As a result, this free electron will be attracted by the positive side of the voltage. As a result, we can find a flow of electron. Inversely, we will get a flow of current. That means by applying voltage V1 and V2, we can get a current. So this is the building blocks of creating a MOSFET. And nowadays we don't use this type of structure because it is quite complicated structure. We have our modern day 3D structure. The new structure is the following. The main idea of that structure is we want our all of the terminal with pointed upwards. This is why we have our new structure, and the new structure is the following. This is our metallic plate. Nowadays we don't use a metallic plate, we use a polysilica, and in this metallic plate has a name on it, and this terminal is called a gate. And then we have our dielectric, and this dielectric, in this dielectric we use a silicon dioxide. And then we have our p-type semiconductor. Now the remaining terminals are A and B. How to create these terminals? To create this terminal, we use a heavily doped n-type semiconductor. And one of them is called drain, and one of them is called source terminal. So this is a present 3D structure of a MOSFET. Now, the one may ask, if I apply a voltage VG on the gate terminal, previously which was V1, will we get a current for any amount of VG? Well, the answer is following. So our first observation, we we fix a drain voltage. For example, we fix a drain voltage. Now, we will insert a new voltage VG, what will happen? So if we provide a new voltage VG, we will have initially we will have a negative ions, which is already present in the PTF semiconductor. So there will be no channel at this moment. There will be only negative ions, so it will create a depletion layer. As soon as we suppress some amount of voltage, I call it threshold voltage, we can see a minority of free charge carrier, or I can say we can form a channel. That means we can form a channel when we suppress the threshold voltage. And as soon as we are creating this channel and our drain voltage is already connected by a battery, then we will get a current. And this current is called drain current. So that means intuitively we can say if Vg equal or greater than V threshold voltage, we can get a channel. And if our drain voltage is greater than 0, which will create a current, which is drain voltage. So intuitively uh, we can plot this. So intuitively we can plot like this. This is Vg and this is Ib. So one thing I forgot to mention that all of our voltage is measuring with respect to the ground, meaning that uh, and our source terminal is also connected to the ground. So meaning that we are measuring all of our voltage with respect to the source. So instead of VD, we can write VDS. Instead of VG, we can write VGS. So as I have said, when VGS is greater than or equal VTH, we will form a channel, and that channel is responsible for flow of current. And this, if we increase VGS more and more, this area of a channel is act like a resistor. So we will get more and more free carriers. As a result, our resistance will be dropped. So that means our current will be increased. So if we say VGS is more and more, the resistance which is around this length, channel length, will drop. As a result, our ID will increase. So intuitively, we can plot that at initially, there will be no current because at initially there is a no gate voltage, then there is no of the channel formation, so the current is 0. As soon as we suppress the threshold voltage and we increase the VGS more and more, the resistance will be dropped, and ID will increase. But we don't know what will be the function. It may be a exponential function, maybe quadrature function. We don't know. But as far I know, on our intuition, from our intuition, that if we increase VGS, we can have a threshold increase of current after one threshold. So I think that's it for this session. Thank you very much.